Static friction. Friction is the force that tries to resist the relative motion of two surfaces that are in contact. So what it tries to do is if an object is resting on another surface, it tries to keep that object from moving across the top of the surface. It's a little bit tricky because it doesn't necessarily mean that it tries to keep the object from moving as a whole. It's about the relative motion between the two surfaces. To illustrate this problem, imagine a truck. Here's the truck, okay? And in the back of the truck, you have the truck bed. And let's say you put a crate in that truck. The friction between the crate and the truck isn't keeping that crate from moving. What it's trying to do is keep it in that location in the truck bed. So if this truck starts to speed away, the friction will actually make the crate move. What it tries to keep it from doing is sliding this way or that way on the bed itself, so that hopefully later, if the truck is over here, then the crate is resting in the same location. Now the friction may not be great enough, like if you slam on the brakes, the friction might not be able to resist that motion, and the crate could end up sliding up to the front. Or if you accelerated too quickly from a stop, it could end up sliding to the back. But what it tries to do is it tries to keep the crate from moving relative to the surface it's resting on. Why does that happen? Well, no matter how smooth you might think surfaces are, if you could look at them closely enough, you'd realize there's some level of bumpiness. So if you have a bumpy surface in contact with another bumpy surface, I think you can see if you tried to pull this surface across this surface, the bumpiness would stand in the way of the motion. So regardless of how smooth it seems like, there's still going to be some friction. There's going to be some level of contact there that keeps one object from moving against the other object. Now it resists it. The forces involved may be large enough to allow the thing to move across the surface, but there's a little bit of a resistance there. Now, not all materials are made the same. They might be hard, they might be soft, they might not be that bumpy, they might be very bumpy. And so friction really first depends on the materials of the object and the surface that are in contact. That's not the only thing the force of friction depends on, though. To understand the second thing the force of friction depends on, I ask you to think about this situation. Imagine you have a textbook sitting on the top of your desk, and you try to slide that textbook across the desk. You can imagine it, push it, whatever it takes, some level of force. Now imagine instead your friend comes along and stands on your textbook. So there he is. He's actually put his foot right on your textbook. There he is. There's his head. Now imagine trying to push on the side of that textbook and move it now. Because your friend is standing on the textbook, it's going to make it much harder to slide it across the floor. So you might make the mistake of thinking, well, isn't that, so then the force of friction also must depend on the mass of the object. But that's not quite right. Because imagine another situation where instead of standing on it, they pull up on the textbook using a pulley or something like that. So there they are. They're holding some pulley. It's a little silly, but you get the idea. Now it's going to be much easier to push that textbook across the top of that desk. In both of those situations, the mass of the textbook itself hasn't actually changed. So if we want to really think about it, what's the best measure of how much contact or how much force of contact there is between the surface and the object that's resting on the surface? And the answer is, it also depends on the normal force. If we recall, the normal force is the force required to keep the object from moving, one object from moving through the surface of the other object. And in those different situations, if the normal force was larger, that means there's a large force pushing up from the surface on the object to keep it moving through. That means there's a lot of contact between the object and the surface. Alternatively, if there's a very small normal force, then there won't be that much contact between the two surfaces. Static friction specifically means that the object and the surface are not moving relative to each other. Again, not that they're not moving. The truck could be moving. The truck carrying the crate could be moving across town, but if the crate isn't sliding around in the back of the truck, the crate and the truck bed are stationary relative to each other. So static friction refers to a situation when the object is not moving relative to the surface. In that case, we can come up with an equation for the force of friction. The force of friction is less than or equal to something called the coefficient of static friction. And it gets that funny U symbol that's called mu, times the normal force. This coefficient of friction, try that again, the S there meaning that it's a coefficient of static friction, is our way of taking into account everything that we can't think about that's too complex with regard to the materials involved. So this is a property of the materials. And Fn here refers to a normal force that we've been using throughout the unit. This formula is a little bit tricky. It says less than or equal to. It doesn't say equal to. So what that means is this FF, calculated from this formula, should be thought of as a maximum value. Again, let's go back to our scenario where you've got a book resting on top of a desk. If you push on the side of that book with a 2 Newton force, and then let's just say, for the sake of argument, you've done this calculation and you've seen that FF max is equal to 10 newtons, that doesn't mean that the force of friction pushes back with a force of 10 newtons. This is your applied force. This would be your frictional force. What that would mean is you push lightly on the side of the book and friction resists you so hard that somehow it pushes the book back towards you and accelerates it. That doesn't make any sense. When you push on the side of a book, it doesn't all of a sudden start moving towards you. So remember, this is the maximum value that frictional force can take on before this object is going to slip, start moving, and stop being static friction and become what we call kinetic friction. What the actual frictional force does is it matches the applied force. And so we have a less than or equal to here because we have to remember that the frictional force is only as big as it needs to be to resist the motion. So we have this force of friction, depends on the type of material involved. We put that into the coefficient of static friction. And the normal force, how much contact there is between the two surfaces, or the force that the surface has to use to hold up the other object. And that gives us an idea of the maximum force we could apply before this object would start moving. We're going to deal with if it starts moving in a subsequent video, so right now we're just focused on that. But then within that, we remember that that's the maximum value it can take on. It's only going to be as big as it needs to be to keep the object from moving. Let's see what that looks like in an example. A 10 kilogram block is resting on a table with a coefficient of friction of 0.48. Here's my 10 kilogram block. And my mu is 0.48. Determine if the object will move when the forces are applied to the block. Also determine the actual force of friction in each case. So for A and B, I can do large parts of this problem together, scenario A and scenario B. In scenario A and B, the gravitational force is negative 98 newtons. Fg equals negative 9.8 newtons per kilogram times the mass of 10 kilograms. And the normal force that's keeping this block from moving through the surface then is going to also equal 98 newtons. So then you're going to push on the side of this block with either 30 newtons, we'll focus on A first, and then in B we'll push with 100 newtons. And the question is the force of friction able to be big enough to keep that from moving? Our formula for the force of friction says that it's less than or equal to 0.48 times 98 newtons. Okay, sorry for that pause, but I was running out of battery, so I need to deal with that. So my force of friction is equal to my coefficient of, or is less than or equal to my coefficient of static friction times my normal force, which I put there. And that means it's less than or equal to 47 newtons. So if I consider my two cases, in A, my applied force is 30 newtons. That's less than the maximum 47 newtons that the force of friction can take on. So what that means is the force of friction can be big enough to stop the object, and so no, it doesn't move. Now the second thing here says determine the actual force of friction in each case. Well, this is just the maximum, right? This isn't the actual value. If you push on the side of this crate with 30 newtons, the force of friction will have to equal 30 newtons to resist that push. So in A, the actual force of friction is 30 newtons, not the maximum value 47 that was calculated. Alternatively, in B, you're applying a force of 100 newtons. That's greater than the 47 newtons that is the maximum force of friction that's possible. And what that means is the force of friction can't get big enough to stop that applied force, and so yes, the object moves. C is an entire different can of worms. The problem with C is that the applied force has both an X and a Y component. The applied force has a vertical component, and so the normal force isn't just going to stay as it is. That applied force, it's like you're pulling up on a string on this object. So here's our 10 kilogram object. The force of gravity isn't going to change at negative 98 newtons. But this time it's kind of like you're pulling up. So some of that force of gravity is going to be supported by the applied force. 75 newtons. What angle did I make it? 30 degrees. This is going to balance against gravity, this section here, the Y part. And this is going to be the force that's trying to make this object move. I think it's hard to look at this on its angle on the free body diagram. So let's take it over here, break it into components, and then put it on as if it was two separate forces. This angle is 30 degrees. This is my opposite. So this one's going to be 75 newtons sine 30, which it works out to 37.5 newtons. So we'll just take all this out. 37.5 newtons. On the other hand, this one is 75 cos 30. Which works out to 65 newtons. Which means we're still pulling with 65 newtons here. Now the normal force, Fn, is the only force that's left to balance out this vertical part. So the gravity's pulling down with 98. The string or person or applied force, whatever it is lifting up a little bit by 37.5. How much is left for the normal force? Well, really what we're recognizing is that in the vertical direction, the net force is equal to 0. And that's going to be equal to negative 98 newtons plus 37.5 newtons, that's this guy, plus the normal force, which will have to cancel out the other part of that. That means that the normal force works out to be 60.5 newtons. Now my force of friction has to be less than or equal to my coefficient of static friction times my normal force. In this question, that was 0.48 times 60.5 newtons. And that means that it's less than or equal to 29 newtons. So the biggest force of friction that can resist this pull is 29 newtons. But I'm pulling with 65 newtons. So since 65 newtons is greater than my biggest, since my force applied is greater than my maximum force of static friction, my object will move. Now you'll notice that in B and C, I avoided talking about the actual value of the frictional force. And the reason being is once the object moves, then we have to use a new formula. The force of friction becomes equal to the coefficient of kinetic friction times the normal force. And you'll notice in this problem, this UK was not given. So the truth is in B and C, I can't come up with the value of the frictional force because I don't have the given information. I don't have the coefficient of kinetic friction. The good news about that is that you'll notice in this formula, and we'll talk about this more later, an equal sign is here instead of a greater than or less than kind of business. So this formula will always give us a definite value for the force of friction if something's moving. Let's look at one more example. A fridge magnet of mass 25 grams is placed on a fridge generating a magnetic attraction of 0.4 newtons. So here's our 0.025. I'm going to change that so it's readable. 0.025 kilogram fridge magnet. I know the dimensions don't look right, but it's hard to draw and put that mass in at the same time. It's attracted to the fridge with 0.4 newtons, which means if it wants to go that way that badly, right, if we think about this as the force of attraction, then what is the force that's keeping it from moving into the fridge or keeping it from going right into becoming part of the fridge door? And that force is a normal force. Now the other forces acting determine the minimum coefficient of static friction that will allow the magnet to stay on the fridge. The other forces acting on this magnet is a force of gravity that's trying to pull it off the fridge. And since we have a normal force, we can surmise that it's the force of friction that's keeping that force of gravity from pulling it down. Force of gravity here is going to be negative 9.8 newtons per kilogram times our mass of 0.025 kilograms. Or 0.245 newtons. And so if the force of friction is going to resist that motion pulling it down, then it's going to have to be equal to it. I'm only really focused on magnitudes here because my force of friction equation doesn't really take negatives into account anyway, so I'm just really looking at the size of these numbers. Force of gravity pulling down, I guess, would be negative 0.245, and so the force of friction up is 0.245. Anyways, I have FF, and I have Fn. All I'm missing here is mu. So my force of friction is 0.245 newtons. That's less than or equal to mu times 0.4 newtons. I'm just going to change that to equal to. And so I get a coefficient of static friction of 61.25. Oops, let me try that again. 0.6125. And those are both in newtons, so the thing about a coefficient of friction is it's unitless, which means us and the Americans will agree on exactly the value of this thing. Anyways, 0.6125, and that's the coefficient of friction for this situation. Keeping in mind, though, any coefficient of friction that's greater than that will also keep the object on the fridge. So the question says, what is the minimum coefficient of friction? Well, if the coefficient of friction is bigger than 0.6125, then the force of friction you're going to see is going to be bigger than that. And as a result, this value right here represents our minimum. So that's static friction. And we'll go on to Kinect in the next video.